Okay, so maybe I can start. So
Yeah, go ahead.
um, uh, thanks to Sharnu for organizing this seminar and giving me the opportunity to talk about my work that I did with um, John Chalker and David Logan at Oxford. And I also must acknowledge EPSRC for funding my postdoctoral research here at Oxford. Okay, so as the title says, I'm going to talk about many body localization as a tale of correlations and classical percolation on Fock-space. So what is MBL and why do we care about it? Put very simply, many body localization addresses the question of Anderson localization or the fate of Anderson localization upon adding interactions between the quantum particles. The reason we sort of care so much about it, or it has become a very active area of research in the past decade or a bit more, is that we have now understood that MBL systems violate the conventional paradigm of statistical mechanics and thermodynamics that many of us sort of grew up to hold very sacred. And crucially, they do so in a very robust fashion, in the sense that MBL is a true phase. You don't actually need super fine-tuned parameters or models to actually show MBL. So naturally, understanding the conditions under which you may or may not have the possibility of having a robust and stable MBL phase is of importance. So the central point that I'm going to make in this talk is that there's something called maximal Fock-space disorder correlations. I'm going to explain this and its implications in considerable detail in the talk. So these maximal Fock-space disorder correlations turn out to be necessary conditions for stabilizing an MBL phase. Um, and I'll basically show how we go about building a self-consistent theory, which actually shows this. And then I'll present a couple of sort of side things which support this finding. Okay, so with that, let me go to the plan of my talk. Now, the first part of the talk is called a lightning review of many-body localization, but in a few slides, it's almost impossible to review many-body localization. So what I'll do is I'll give you my personal take on why I think MBL is interesting. And more importantly, I'll try to motivate the questions that we ask and try to answer in these set of words. Okay, then I'll move on to the second part of my talk, which is about these Fock-space correlations that I just mentioned. And I'm going to describe that, first of all, why we sort of think that studying MBL on the Fock-space is one of the useful ways of doing it. Why is it not a standard Anderson localization problem on a high-dimensional graph? And how do these Fock-space correlations take center stage? Um, then I'll move on to a slightly different view of this problem as a classical percolation problem on the Fock-space again. And this will basically help us give a physical picture for what I'm going to describe in the part about Fock-space correlations. And finally, if I have time, I'm going to switch gears and talk about a single particle Anderson localization problem on high dimensional graphs again, but with strongly correlated disorder. In fact, these disorder correlations would mimic the disorder correlations on the Fock space of a many-body system. And the motivation behind studying this was that, arguably this is a more controlled setting for studying the effect of correlations in the sense of distilling them out. All right, so that's the plan of the talk. And let me then start at the very basic. One of the crowning jewels of modern physics, condensed matter, statistical mechanics is thermodynamics. We understand how classical thermodynamics works. We know that a complex system with many microscopic degrees of freedom can indeed be described via a few macroscopic observables, and that's basically thermodynamics for us. And the bridge between thermodynamics and microscopics is given to us by statistical mechanics. So then you can ask the question about thermalization or the emergence of thermodynamics in isolated quantum systems. This, on the face of it, is actually quite a non-trivial question because we know that quantum dynamics is unitary. So how is that compatible with the state of the system being described by something like a Gibbs ensemble, which is inherently a mixed state? And the basic thing that happens here is that isolated quantum systems thermalize locally. So for a small subsystem S, the rest of the system, which I called S bar here, acts as a path. And the key idea here is that of the eigenstate thermalization hypothesis, which basically tells me that if you give me an eigenstate at energy E, then if I trace out all the degrees of freedom, barring a few, which are supported on this subsystem S, then this reduced density matrix indeed looks like a Gibbs ensemble. And this temperature of the Gibbs ensemble is actually set by the energy of the eigenstate measured with respect to the Hamiltonian. Now, this immediately leads us to concluding that if I actually prepare an out of equilibrium initial state and look at some local observable, again, supported on a few sites or supported on this small system S or small subsystem S here, then at very long times, it would be again given by a Gibbs ensemble, where again, the temperature would be set by the expectation value of the energy of the initial state. Now, one thing that I would like to make very clear here that what we are talking about here is about states which are in the middle of the spectrum. So these are far, far away from the ground state. And in principle, these are what we would call close to infinite temperature states. And it's also sort of known that these ideas of thermalization go hand in hand with ideas of entanglement in such systems. And these states generically have volume law entanglement. Of course, there are exceptions, but I'm not going to talk about them. Now, this is all very nice. And the question is,
can I ask you a question? Sorry. So
sure,
I keep hearing this idea that if once you take states in the middle of the spectrum, it is like an infinite temperature. But if I give you a free fermion and I take a state in the middle of the spectrum, it's a Fock state, and I can have states there which do not have volume law entanglement. However, if I write the thermal density matrix, I will get a volume law entanglement. So I've never understood why people talk about it's okay to talk about it when you are talking about local correlations, but I'm not sure these two are equivalent statements when you talk about entanglement.
No, so I would sort of disagree, and because you took a very quote unquote fine-tuned example of free fermions. Free fermions are not generic. So this is for a generic system that you have a non-integrable interacting system.
No, but I'm just saying that the general idea that a state in the middle of the spectrum is equivalent to a density matrix at infinite temperature is not
locally.
For local operators, it is correct. But for entanglement, it is not a local operator. But entanglement and volume law entanglement you're talking about, entanglement is not a local operator. So for that, these two answers will not be same, a density matrix answer and
I'm claiming that for generic systems, it would be. For non-integrable systems, it would be. For free fermion systems,
it might still give you volume law, but the two answers are not same. A density matrix, I take a density matrix, I calculate its entanglement, and I take I take all eigenstates with some equal measure, and I calculate entanglement of each eigenstate and then average that entanglement. These two processes are not the same. It might give you volume law in both cases, but it will not give you the same answer.
Okay, this I agree with, and in fact, very recently there has been, or maybe there are more, but I know a couple of works where they actually address this issue about a completely random state drawn from, a completely random state drawn from some Haar measure that actually has an entanglement, which is basically what you would call, the page corrected value of the maximal entanglement, and a sort of infinite temperature state from a local Hamiltonian actually still has a volume law entanglement, but it has a small correction. And that comes about because you have, if you think of the wave function on the Fock-space, that has some holes in it, and you can actually calculate the corrections to this. After the talk, I can tell you the right.
Go ahead. This was probably just a slight technical point, but go ahead. Yeah.
Okay. So, all of this sounds very nice.
Sorry, can I clarify what Rajdeep just asked and your answer? I'm not sure I understood. So if you're really thinking of infinite temperature,
Mhm.
The density matrix I'm looking at is just the sum over eigenstates outer product, right?
It's really just identity, proportional to
That's
identity.
what I'm saying. So then what is
Yes.
the statement you just made about holes? I didn't understand. You said something about if you look at the infinite
Oh, I
temperature
see.
density matrix
Right.
of, that's my point. I mean, you said something which didn't make sense if I think of that as just the identity.
Okay, I see. Okay, so let me clarify that. So if you take a local Hamiltonian and take an eigenstate, which say is from the middle of the spectrum, and then you say trace out half of your system. Okay, that's what you would do to compute the volume law or compute the entanglement entropy between, say, two halves of the system. So then you still have an extensively large system, and you are looking at the reduced density matrix of an extensively large subsystem. This
You're saying you take the infinite temperature ensemble, or you take one state. As you said something about
no, you
infinite
take
temperature.
one.
That's what you take one state
You take right. So you take one
ah,
state
in the middle of the spectrum.
and in the middle of the spectrum, and you compute the entanglement entropy
You
of
compute the
between two.
bipartite entanglement entropy of the reduced density matrix on one
Precisely,
side. Yes.
precisely,
And then
precisely.
what is that to
And
be compared with? That will give you volume law, but it's
that
what is the different volume law that you're comparing it to and agreeing with Rajdeep? I just want to be clear about this.
if you actually took a random state, because a random state barring some fluctuations is like an infinite temperature state. So you'd actually take a state and you take a 2 to the power L or
Oh no, but
the
oh,
hill.
I see. But I didn't think Rajdeep, is that what you were talking about? I got the impression that was not. I'm confused.
Here is my statement. Okay, take all whatever states in the middle of the spectrum. Take
Yes,
one state,
yes,
calculate its bipartite entanglement
correct.
entropy. Now
Yes,
average over all states with equal measure. Okay, this
average that quantity over all states,
all states, whatever in some
not
middle
just
of
in
the,
a band in the middle of the spectrum, but over literally all states.
no, let's take in the middle of the spectrum for all
Some
I care.
band in the middle of the spectrum.
Middle
Fine.
of the spectrum. Okay,
Ah,
this
ठीक है.
is not the same as you take all states in that spectrum, okay,
Mhm,
band,
mhm.
write down a density matrix which is 1 over number of states shy, and then
Just for
calculate
that band. Uh-huh.
just for that band and
Uh-huh.
calculate its entanglement entropy. These two things are not same, because when you do this partial tracing of
Yes,
to get reduced density matrices, okay,
yes.
the
Yeah,
SVDs
this part I
frequency.
followed. This part I followed, but
That's
I
all
didn't
I was.
understand how this relates to the random vector in a Hilbert space.
No, that I don't know, but this is what
Ah,
I was
this I
asking.
understood. So it seems to me there are three things y'all are talking about. One is what Rajdeep defined. One is
Right.
what you just said earlier, Sthitadhi. And the third is the
Yes.
random vector. And
Right. So
random
exactly, there are
vector,
three
of
things
course,
here.
is going to be different, I feel, from a local Hamiltonian's eigenstate, right? Random vector is
But
not,
but
yeah,
it's just a very small difference. I mean, and that
yes,
has been computed in some recent
yes,
work.
yes.
Yes.
Because for a random vector, there is some theory based on, as you said, random matrix theory and page entropy and so on.
Right.
Yes.
Yes.
But
So okay. So
Albert
all I wanted to
something
say was
different. Yes. Okay. Go.
yeah. So all I wanted to say was that these eigenstates have a volume law entanglement entropy, and locally they might look like infinite temperature states. I actually have not made the claim that the entanglement entropy or the bipartite entanglement entropy of these, middle of the spectrum eigenstates actually equal that of infinite temperature states. I only said that
Yes.
they have a volume law, but locally they
Yes.
can look like infinite temperature states in
Yes.
terms of
Okay.
local observability. Okay.
Good.
All right. So this all looks sort of quite all encompassing, but you can ask the question that can quantum systems fail to thermalize? And the basic intuition would be that you need to stop the different parts of the system from communicating with each other. If you can do that, then it's clear that if I take a small subsystem here and it's sort of not in communication with the rest of the subsystems or the rest of the system, then it's not going to thermalize. And that immediately sort of points us towards Anderson localization. Now, Anderson localization, as we all know, is now more than 60 years old. It tells us that non-interacting particles on a disordered lattice are exponentially localized with basically virtually no correlations between the localization centers and the energies of the eigenstates. And this is indeed a sort of, I dare say, a trivial example of a quantum system which fails to thermalize. But then again, you can sort of put on or be a devil's advocate and say that, well, okay, this doesn't satisfy me because Anderson localized systems are very special because they're non-interacting. And that gave rise to this, or in my opinion, that's one of the interesting things about this field of many body localization, because it is asking the question of localization in a sort of generic setting, that you have disorder and you have interactions, and you're asking that can this localization still persist? And by now we sort of we sort of understand that many body localization does exist in 1D. Higher dimensions are still sort of controversial, but at least in 1D, we think that they definitely do exist. And that raises quite a few questions. For example, because they don't thermalize, how do they actually admit a StatMech description? And if I do a quench, or if I start off with some non-equilibrium state, then what kind of non-thermal ensembles do they go to? How do they do so in time? And there are questions about suppressed transport, suppressed growth of entanglement, and so on and so forth. Another field which actually interests me quite a lot in this is that MBL can actually help you stabilize new phases of matter which have no simple analog in equilibrium StatMech, such as infinite temperature glasses. Again, I'm saying infinite temperature, but all I mean here is the middle of the spectrum, time crystals and periodically driven systems, and so on and so forth. Okay, so this is sort of the, sure.
So, but on the left-hand side for the thermalization problem, there was no disorder that you had in mind, right? And I did not get
you
the
can
connection.
have disorder. You can have a random system, but you can have a system where all the couplings and the fields are random, but all of them are sort of of the same scale. There is no basis in some sense that's preferred.
Right. So but the thermalization
yeah.
may fail even in absence of disorder. On the other hand, what I understand that in Anderson localization, you need disorder to see the localization. So I didn't quite understand the connection between these two different scenarios from the perspective of in one case.
When you say that thermalization can fail, even in the absence of disorder, there are definitely examples of such systems, but my sort of opinion would be that they are quite fine-tuned. An example is free fermionic systems. Another example is integrable systems. But the point is that these are all fine-tuned systems. If you move away from the integrable point, then those systems would then start thermalizing. You also have examples of disorder-free localization. For instance, you can have what people call quantum disentangled liquids. You can have basically two species of particles, or two species of particles or spins in a system, and one of them is sort of heavy and slow, the other is light and fast, and the fluctuations in the latter actually, the quantum fluctuations in the latter give you some effective disorder for the slow degrees of freedom, and so on and so forth. But these are all fairly fine-tuned and specific models. If you disturb these models by adding some term, maintaining sort of the locality and so on, more often than not, these systems do indeed thermalize. So all I'm saying is that the intuition is that if you can stop different parts of the system from communicating to each other, you can stop thermalization. And sort of one of the most glaring and robust, quote unquote, ways of doing it is via having localization due to disorder.
Okay, thanks.
Okay, so then the question is about minimal models, and for ergodic and or chaotic quantum systems, we sort of understand. Again, this is basically this is a statement with some error bar, that a many-body Hamiltonian is, or many properties of many-body Hamiltonians are well captured by random matrix theory. And of course, you need to put in the information about locality and the fact that this has extensive number of degrees of freedom. That gives you some scalings for the random numbers that you can put in your random matrix and so on. But often, theories based on random matrix theory is enough to tell you about some universal properties, such as level statistics that follows Wigner-Dyson statistics showing level repulsion. You have a ballistic growth of entanglement entropy from initial unentangled state, or you have the ETH satisfied with local observables, expectation values being a smooth function of energy, and so on and so forth. But for many body localized systems, of course, these things are completely different. For example, level statistics actually is Poissonian. The entanglement entropy grows logarithmically in time. Local observables actually do not satisfy ETH. If you take a many body localized system and plot an expectation value of some local observable as a function of energy, it looks something like this. And the point is that, what is a minimal many-body Hamiltonian with a stable MBL phase? Now, this on the face of it is a very difficult question because we also sort of don't know what are the minimal ingredients that you need to have a stable MBL phase. So we actually take, although this is the question we want to answer, we understand that this is, a very difficult question. So we try to sharpen it a bit and ask a slightly different question, which is we take models that are known to host MBL phases and we look for the necessary ingredients that stabilize the MBL phase they're in. And we'll try to contrast it with situations where we know that a many-body localized phase does not exist, even though the model is disordered and so on. And of course, this is not just simply saying that, if you just take the disorder strength large enough, will the MBL phase come back? No. So there are two kinds of models. One where at some finite disorder strength, you have an MBL transition, and beyond that, you have an MBL phase. And you take models where, no matter how strong the disorder is, you actually don't have an MBL phase. And we would like to understand what distinguishes this. And that's basically the first part of the talk. And let me get on with that. All right. So we consider the problem of many-body localization on the Fock-space. And that is because any many-body Hamiltonian can actually be written as a tight-binding Hamiltonian on the Fock-space graph. For example, if you give me a spin-half system, I can basically club together all the terms in the Hamiltonian that are made up of sigma z and identity operators and call it the diagonal part of the Hamiltonian in the basis of sigma z product states. And I can have a spin flip term, which basically gives me the quantum fluctuations. On the basis defined by the sigma z product states, I can write down the Hamiltonian as the tight-binding Hamiltonian on the Fock-space graph, where each node I is a spin configuration of all the n spins in my system. It has some energy EI, and this spin flip generates some hopping between the different Fock-space sites, which I call TIK. Now, even before specifying the specifics of the model that I am going to look at, there are some properties of this Fock-space graph that you can immediately understand. So one is that this graph is exponentially large in system size, and that's just reflecting that a Fock-space of a many-body system or the Hilbert space of a many-body system is exponentially large in system size. Then the next point is that the connectivities on this graph are typically extensive. So what that means is if I take any spin configuration, from that, via these spin flips, I can go to order n other Fock-space sites, or n other spin configurations. And the other thing that you can also immediately see is that the effective variance of these Fock-space site energies, and I'm going to call this the Fock-space disorder, henceforth, that actually has a variance which is linear in system size. But that, and I'm going to say more about this, but what you can almost certainly show for local disordered Hamiltonians is that the distribution of these EIs is actually a Gaussian with a width or the standard deviation which scales as the square root of the system size. And if you put the fact that the effective variance of the Fock-space site energies is linear in system size and the connectivities are typically extensive, you can also immediately infer that the total density of states also has a variance which is extensive. So within this,
sorry,
sure.
one question. This effective variance scaling as n, is this a statement about disordered systems only? Because this, for example, not be true if I just give you some arbitrary potential energy, right?
Okay, so that's actually a very good point. So This will be true also for a non-disordered system. And there, what will give you this variance is the fact that you have some configurational disorder on the Fock-space, right? So imagine that I take all the some spin-spin couplings, all of them uniform, and some fields, all of them uniform. But then on the Fock-space, there is some configurational disorder, which is just the difference in the spin configuration. So that is also going to give you a effective disorder on the Fock-space, right?
Is that,
And
does that mean, because
that also has the same scaling.
this statement doesn't seem to be, has that been shown by someone, or is it something that people assume? Because what you are doing here is you are thinking of it as a sum of independent random variables, right? Somehow that's why your variance scales as n. I mean, the overall.
But it is independent, right? I mean, actually, okay. So let me say this. First question, yes, it has been shown, and there is a derivation of this in the paper that I cited that we wrote last year. So it has been shown, yes.
That for
actually show this
any non-integrable Hamiltonian I take, and I write it as an effective on-site energy of Fock-space configurations, the variance always scales as n.
Yes.
Do you need a finite dimensional local Hilbert space?
You do need a finite dimensional local Hilbert space, and
that's
you
what
also
I think
need,
Rajdeep is not. Rajdeep, if you have a finite dimensional local Hilbert space, that will restrict this effective.
Yeah. So
that will give
for
it.
example, that was my next question going to be, both. Does it work for bosons? Yeah.
Probably not. So you need a finite dimensional local Hilbert space, and another way in which you can break this, and this is also something that we have shown in a different paper, is if you have long-range couplings. So if you have power law hoppings or power law interactions, you can actually break this.
Okay.
But okay, so here I'm sort of restricting myself to local disordered short-range Hamiltonians. Okay, so within this setting, the simplest model that I can write is the so-called quantum random energy model, where the spin flip terms stay as I had written before, but to each spin configuration, I actually assign a completely independent Gaussian random number with a variance which scales as n times there's some effective disorder strength W. You can set W to 1 if you want. Of course, I cannot write.
Just to clarify,
the
thought of as a graph, this is a graph whose coordination number increases weekly, logarithmically with the size of the graph. Is that correct?
That's absolutely correct, because the size of the graph grows exponentially with the system size, whereas the coordination number grows linearly with system size.
So almost fixed coordination or bounded coordination, but there's a log.
There's a log. So
yeah.
In fact, if you set the okay, so you notice that the spin flip terms actually decide the topology of your graph. And this kind of a spin flip term, which is just sum over sides sigma x at the side, that actually gives you a precise hypercube. You can make similar statements for an XXZ type model, but there it's not an exact hypercube. But for this, it's an exact hypercube.
Right. Okay.
Okay. So,
well, hypercube. So that seems to also bring in something very non-generic then, which is bipartiteness.
Well, okay, but all of these results, or what I'm going to present, holds also for XXZ type models, which is not a precise hypercube. Yeah.
Yes. Okay.
Okay. So then the point is that this is the quantum random energy model, and this is something that has been studied quite well. And the essential result here is that if you take a phase diagram like this, where on the x-axis you have the disorder strength W, or W over gamma if you want, and on the y-axis you have the energy density, then basically at all energy densities you have an MBL transition, except at zero energy density. Zero energy, the system is always ergodic. This is something that I'm going to harp quite on, but let me introduce another model, which is basically a disordered quantum spin chain, which is non-integrable. So you have a disordered coupling between the Z components of the spins nearest neighbor. You have a disordered field, which also couples in the Z direction, and you have the spin flip terms given by sigma x. Now, what you can show in this model analytically is that the Fock-space disorder is actually not uncorrelated. In fact, this is something which I will call maximally correlated in a few slides. But for now, it's enough to see that it's not correlated. And for this model,
Sorry, what was
the phase
the model
diagram,
where? Sorry, what was the model where E equal to 0 was not going to be MBL? That was the one with the
the
local
quantum
flip.
random energy model.
Just the quantum. Okay.
Okay,
No, but,
so
okay.
right. So the crucial point is that both the two models that I'm sort of distinguishing here have the same local spin flips.
Yes.
The diagonal part of the energy or the Hamiltonian is different between the two models. So one is the quantum random energy model is that all the spin configurations, have some random energy. But
Yes.
here there is a local interaction which gives you the local interaction and local
Right.
fields
So
which
instead
give
of
you the
uncorrelated site energies in Fock-space, you have strong correlations now.
precisely. That's the point I'm going to harp on quite a bit. Okay, but what you notice is if you go from the quantum random energy model to the disordered quantum spin chain, the phase diagram basically looks something like this in the blue, as I've shown it with this blue curve. And indeed, you have a finite disorder string for an MBL transition, 0 energy density. Now, you might say that, well, okay, this is just one particular energy density. Why should I care so much about it? The two models are basically the same. But remember that the density of states actually has a scaling in energy, or the density of states has a width, which scales as the square root of system size. So what that means is if I then decide to look at things in energy densities, the density of states actually in terms of the energy densities has a width which scales as 1 over the square root of system size. And what that means is in the thermodynamic limit, it actually becomes a delta function at 0 energy density. So basically all the action is at 0 energy density. At finite energy density, you actually have an exponentially suppressed density of states. So any sort of genetic dynamics would be controlled entirely by the nature of states at 0 energy density. And this is why I would say that these two models are qualitatively and fundamentally different in the sense that the quantum random energy model actually has no MBL phase, whereas the disordered quantum spin chain indeed has an MBL phase.
So,
In fact, I would go.
one question is that MBL red curve that you are showing, which is for the random energy model, is it known? How does it go with the disorder strength?
Yes, it's basically this. The EC is 1 over W.
Okay, it's 1 over W. Okay.
Right. Yeah. Okay. So, all right. Now, I would go as far as saying that these mobility edges that there are in the literature are somewhat misleading because if I sit at some disorder string that I'm pointing with my cursor, it would suggest that in order to get to an MBL phase, I need to go to an energy which is extensive. Whereas because the density of states scales as square root of the system size or the width of it, how do I know, how do I know that there are no mobility edges at energy scales which are going as the square root of system size? In fact, I should expect mobility edges at energies which are square root of system size. Now, the reason sort of this has become a part of the, or looking at energy densities has become a part of the lore is number one, because we are all sort of trained in equilibrium statmech where energy is an extensive quantity, and it almost seems natural that yes, energy is an extensive quantity, you should scale it by n, and that's the right way to do things. But here, what one should really care about is the width of the density of states. And that's why scaling energies by an extensive quantity is quote unquote not the right thing to do. And I think the second and sort of less dominant reason is that the quantum random energy model is a bit special. You can actually find this 1 over W analytically. But for most of these models, the phase diagram has been obtained numerically. And these are all sort of system sizes of the order of 20 to 20, 24 is sort of heroic numerical calculations. And that really, those system sizes don't really distinguish between n and square root of n.
So,
But okay, so
just one question. Even when your effective disorder is strongly correlated, this holds, this 1 over root n scaling of the density of states holds, because that's
it does.
I see.
It does. You can actually show this analytically
I see.
for for a whole class of models. Yeah.
So Sthitadhi, sorry. So just to understand your statement, does it mean that in the case of quantum random energy, if the correlator of the noise, if I scale with differently with n, do I also get then the MBL phase at the zero energy?
Okay, so as you can see, you have some freedom here, right? Because there is the connectivity which is fixed to n, right?
Right.
And then you're asking that what happens if I change this power?
Right. You usually put that n because you want the energies to be, let's the minimal energies to be extensive in the system, right? In the
Well, no, the fact that the minimal energy is extensive is a byproduct. What I really want is I put the n because I want the density of states to mimic, or the scaling of the density of states to mimic those of local Hamiltonians.
Okay.
So that naturally puts the extremas of the energy band at plus or minus something times n.
Okay.
So that's why I put it. Now, okay, now what you're asking is an interesting question, that if I actually put this n to something different, and I can give you an estimate, and that's basically building on classic Anderson local. Okay, because on the face of it, you can think of this QREM as basically like an Anderson localization problem, because apart from the fact that there are some non-trivial scalings on the graph, everything is independent. And there you know that when everything is sort of order one, you know that the critical disorder goes as the connectivity times the log of connectivity. So then you can put the various rescalings that you want to do and sort of try to find out whether you have an MBL phase or not. So in principle, if you change this power of n from 1 to something else, you can induce an MBL phase at zero energy density. That's something I would agree with. Yes.
Okay, thanks.
Okay. So the point I want you to take from this discussion is that that MBL on Fock-space is not a standard Anderson localization problem on a high-dimensional graph because of the correlations. Second, the simplest model, which actually does look like a standard Anderson localization problem, which is the quantum random energy model, does not have an MBL phase. And it sort of suggests that the presence of Fock-space correlations, such as in disordered local Hamiltonians, is crucial. Okay, so I'll then start talking about correlations in Fock-space eigenenergies, but if there's a question about the general setting, maybe this is more questions about the general setting is a good time to ask. Okay, so if not, let me talk about correlations in Fock-space eigenenergies. So let's consider the diagonal part of the quantum spin chain that I had written. So there is actually, as before, there is a field which comes to the sigma z direction, and there is a disordered interaction between the zz components. Now, as we might have already realized, that the number of random numbers I need to specify this Hamiltonian is polynomially large in n. In this case, it's basically 2 times n. On the other hand, these random numbers actually get added and subtracted with random signs to give you the Fock-space eigenenergies. So if I think of the Fock-space as some sort of a black box where I feed in 2n random numbers and I take out 2 to the power n random numbers, it's obvious that I did not supply as many input random numbers as I pulled up. So they have to be correlated. There is another kind of correlation that you need to worry about here, which is the following. So imagine this blue blob is my Fock-space, and this is a particular spin configuration that I'm looking at. And I want to flip the spin that I have colored in red with its neighbors pointing up. So if I do that, the energy cost that I incur is basically 2 times hi plus the sum of 2 coupling constants. And that's because, they were pointing up. Now consider another spin configuration where the spin in red and its neighbors are in the same configuration, but everything else can be completely different. So in that case, the cost of flipping is again going to be identically the same. But now there are 2 to the power n minus 3 such configurations. I'm n minus 3 because I'm taking out these 3 spins. So what that means is there are order, e to the power n such linked pairs on the Fock-space, which actually have the same energy cost. And this is another kind of correlation that you need to worry about. What this also tells you is that if I actually take a spin configuration and I flip r spins and get to another spin configuration. So let's say I call the initial one I, and then I go to k by flipping any of the r spins. Then if I were to plot the conditional probability distribution of these ek given ei is 0, I actually will get a Gaussian with a width which scales as the square root of r. Now, on the scale of the total, or on the scale of the distribution of all the Fock-space site energies, which actually scales as square root of n, this actually is extremely narrow if r is finite and I take the system size going to infinity. So what this is hinting towards is that the energies of the Fock-space sites at a finite distance from each other are sort of completely slaved to each other. So this is basically the point about correlations being actually present on the Fock-space site energies. But in fact, we can say quite a bit more about the exact form of these correlations. In fact, you can show that these Fock-space site energies actually are described by a multivariate Gaussian. And this is a major simplification because if you tell me that, well, the distribution is actually a multivariate Gaussian, then I only need to know the covariance matrix C. But again, you can come back and say that, well, okay, you have given me the covariance matrix, but it's sort of useless because this covariance matrix is still an exponentially large matrix. So what do I do with this? The next major simplification happens when you realize, or this is again something that can be shown, is that this covariance matrix has its matrix elements depending only between the distance between the sites on the Fock-space. So here, distance basically means the number of spin flips you need to make to go from one Fock-space site to another Fock-space site. So this actually is a major simplification because all I'm saying is that you give me this gigantic covariance matrix and you ask me what is CIK. I actually don't need to know what the spin configurations I and k are. I only need to know what is the number of spins that are different between the two Fock-space sites or the two configurations. In fact, what you can show is that the general form of this covariance has basically three parts. So one is an effective disorder, which comes from the inherent disorder scales that you put in your problem, such as the disorder distribution of the couplings and the fields. Then you have a scaling with system size, which is n. And then you have this function, which we call rho, the reduced covariance, which encodes the dependence on the Hamming distance, which is the number of spin flips that you need to make. Of course, when r is equal to 0, the reduced covariance is maximal, and that's just 1. But what you can show, and this is a crucial result, is that this quantity rho of r comma n generally is a polynomial of order p for a p-spin system. But more importantly, it's a polynomial of r over n. What that means is that if I actually take a finite r and take the limit of system size going to infinity, then this rho of r comma n actually goes to 1. And what that means is that indeed the Fock-space site energies at finite distances are sort of completely slaved to each other. Now, in a talk, I actually can't show you the algebra. So let me give you a numerical plot for this Ising type Hamiltonian. And what I have done here is I have plotted the covariance. I have scaled the x-axis by the system size. And what you can see is that all these data points actually fall on top of each other, more or less. And remember that these are not very big system sizes. So in a way, it's sort of rather nice that it already does this. And what you can also show is that it is indeed a function of this form. So it's a parabola, it's a second order polynomial. That's because this is a 2-spin system. It has at most quadratic interactions and spins. It's a parabola, and it's a parabola of r over n, as I say. And this red curve is the analytic one that you can derive. This coefficient a actually depends on the disorder strength of j and h, which is not particularly neat, so I'm not writing it. But what this establishes is that indeed this reduced covariance is a function of R over N. Okay, but notice that there is another point to be made here, which is that this covariance matrix actually has the scaling N. But in the multivariate Gaussian, what sits on the top is C inverse. So in the N going to infinity limit, the distribution written as here is actually not stable. So to make this distribution stable, and this is a crucial point about how to take the thermodynamic limit in these problems, to make this distribution stable, you need to rescale the many-body energy scales by a quantity which is square root of N. Once you do that and write down the joint distribution of these E tildes, which are the rescale variables, you actually find a perfectly well-defined covariance matrix in the thermodynamic limit. So this rescaling the energy scales with a quantity which is square root of N is going to be extremely important. All right. So until now, what we have is that we understand that for disordered local Hamiltonians, you have correlations in the Fock-space eigenenergies, and we have quite a bit of information on what these correlations look like.
So
I will now
use... I got confused by the why do you need the square root of N? Is just to get that your probability distribution has a limiting N independent.
Yes, and right, and because
that's just what you do for center limit theorem kind of ideas, right? You have many Gaussian variables, right. And
yes, in fact, the scaling here comes from basically the multivariate version of the central limit theorem. I think it's called the Acer-Lissus theorem or something. But the point is that in order to take the thermodynamic limit without breaking or without sort of breaking anything, you actually need to rescale this. Otherwise, things basically blow up. I'll give you another argument for why, in order to keep the problem well defined, you need to, in the thermodynamic limit, you need to rescale your many-body energy square root of N.
When you say there is a thermodynamic limit, you mean what you mean in this context? In this, is that there is a partition function which is extensive, free energy, which would be extensive, and this.
No, all I mean is that when I say thermodynamic limit, I mean the system size should go to infinity and my distributions should remain well defined. So, okay, there are 2 points here. And one is that the distribution of the Fock-space eigenenergies has this width, which is square root of N. And that actually grows with system size. So that basically breaks your C inverse if you go and take the thermodynamic limit. So to stop that, you need to do this rescaling. And the second point, and this is something that I was going to say in a while, which is that it's sort of known that the many-body localized eigenstates are not like Anderson localized eigenstates on the Fock-space graph. They are more of a fractal nature. So basically, the number of Fock-space sites over which MBL eigenstates have support on actually does diverge in the thermodynamic limit, but it diverges with the Fock-space dimension to some power which is less than 1. So to actually detect the MBL phase, you need to look at things relative to, on the Fock-space, you need to look at things relative to the analogous quantity in the extended phase. And I'll present an argument that why scaling these things by square root of N actually does this for you.
Okay, thanks.
Okay. All right, so I'm going to use this information about the correlations into what we call a self-consistent theory of MBL, but I'll be happy to take any other questions on the correlations if there are any. Okay, if not, let me talk about this theory. So what we want to know is we want to prepare a state in a spin configuration, which is one particular Fock-space site on the graph, and we want to know how does it spread out once it's evolved with the Hamiltonian. And this is simply the local propagator on the Fock-space. And what we would like to do is we would analyze it in the frequency domain. Now, in the frequency domain, of course, I can write the local propagator in this fashion. Until now, I have not done anything fancy. And what I've identified is that this self-energy correction has a real and an imaginary part. The real part is just the sort of perturbative correction to the Eigen energies from EI. Whereas this imaginary part, which I call delta I of omega, is the crucial quantity for us, because this is the rate of loss of probability from the initial site I into states at energy omega. So naturally, this is a probabilistic order parameter for the localization delocalization transition. So in the delocalized phase, this quantity delta I of omega is non-vanishing typically, and that's just because that there's a persistent decay of the probability from site I, and a finite delta I basically encodes this rate of decay. Whereas in the localized phase, initially the probability will decay a bit because of a finite localization length in Fock-space or in real space, and then it's going to saturate to some finite value. And because it saturates, there is no persistent decay rate. So this delta I actually vanishes, but it vanishes proportional to eta, where eta is the regulator I put in my theory. Now, let's do a very back of the envelope type calculation deep in the delocalized phase. And it's basically like a Fermi's golden rule type argument, where I say that deep in the delocalized phase, the rate of loss is basically going to be proportional to gamma squared, which is the hopping matrix element, times the number of channels I have in the Fock-space. That's n because of the connectivity or the coordination number of n on the graph. And I have a density of states, which basically goes as 1 over square root n, because that's the normalization that sits in front of the Gaussian. So that basically gives you that delta of omega should be gamma squared times the square root of system size. So you notice that this rate of loss, in fact, diverges in the thermodynamic limit, at least deep inside the delocalized phase. So again, for the problem to remain well defined in the n going to infinity limit, or to make sense of the thermodynamic limit, you need to rescale these energy scales, or in this case, the imaginary part of the self energy, by square root of n. Right. So what we do is we take this delta of omega and write it as a renormalized perturbation series. I've only written the first term, but you can write it for a few more terms. And that's basically a sum over all the neighbors of the site I times the hopping matrix element squared over this denominator. But as I said, that we are going to work in terms of the rescale variables. So once I do all the rescalings, I denote the rescale variables with this tilde. The equation for delta tilde basically has the same form, which is good. Basically, what that means is that there are no dangling factors of n around. And then to do a self-consistent theory, what we do is we take the self energies on the right-hand side of this equation and replace them by their typical values. Once I do that, I can basically obtain a distribution of this delta by transforming over the distributions of these ek tildes. But remember that in order to do that, you actually have to take the joint distribution of all the e's, which encodes the correlations in the Fock-space site energies. And this is how the Fock-space site energy correlation actually gets fed in. Now, the point is that once I've done this, I actually get a distribution for delta tilde, which parametrically depends on the delta typical that I sort of put in by hand. So then we come back and impose self-consistency and say that, well, the typical value that I obtained from the distribution by taking the geometric mean should match with the parametric delta typical that I had put in. So basically, this is the program that we are going to run. Now, the crucial point is the equation written in step 2. And so let's sort of look at this in a bit more detail. So notice that this actually is at least to leading order, this is a sum over Fock-space sites, which are neighbors of I. So these are always at a finite distance away from, or the sort of sites k that participate in this sum are always at a finite distance away from I on the Fock-space. But the maximal correlation for local Hamiltonians means that this ek is only order square root r away from ei. What that means is once I do the rescalings with respect to tilde, the conditional distribution of ek tilde given ei tilde becomes a delta function. What that means is in the thermodynamic limit, Ek tilde is effectively equal to Ei tilde. And this is a major simplification because now the self energy is just a single term. So from here to here, what I have done is I have removed or I've replaced this Ek tildes by Ei tildes following this argument. And then I have a sum over all the neighbors of K, of which there are n of them. So that removes this tilde, and I'm just left with this gamma square. And this is quite a simple expression to manipulate, because now in order to get a distribution of this delta, I only need to transform over this single body or one body distribution of the EIs. So I can do that, and I can impose self-consistency in either phase separately. I'm not showing the algebra, but all of this can be done analytically. And what you find is that the self-consistency of either phase actually breaks down at the same point in the parameter space, which indicates the MBL transition. So I must admit that the MBL transition critical point that we estimate from this theory is a bit off from what's known numerically, but we think that those quantitative corrections can come from the higher order terms. But now let us look at the other extreme limit of the quantum random energy model, where even after I do the rescalings, this Ek tilde remains an order 1 number away from Ei tilde. So basically, all the Ek tildes and Ei tildes can still be treated as independent random numbers, but with a disordered distribution, which has a width which is now order 1 and not order square root n. And then it begins to look like a standard Anderson localization problem on an infinite dimensional graph. But the upshot is that the terms in this sum are all independent. So again, I can compute the distribution of this delta tilde by, because it's a sum of independent random numbers, I can do the standard things about writing the generating function and so on, and compute the distribution. And what we find is the localized phase is never self-consistently stable. And that tells you that the maximal correlations in the disorder is what is stabilizing the MBL phase in the disordered local Hamiltonians. So that brings me to the central result, which is that this reduced covariance at finite distances has to be equal to 1 for many body localization to be stable. That's what happens for disordered local Hamiltonians. Whereas if you go to the other extreme limit of basically no Fock-space correlations, like in the quantum random energy model, you actually have no many body localization. I must say that this is not a sufficient condition for MBL to be stable. Rather, it's a necessary condition for MBL to be stable. And of course, there's a question about what happens at intermediate values of this reduced covariance when the Fock-space height energies are partially correlated. And again, there is some dirty algebra involved, but what you can show is that that model basically is like the quantum random energy model in the sense that there is no many body localized phase. So any sort of randomness or independence in the Fock-space height energies at finite distances actually leads to delocalization. Now, this actually seems like a very counterintuitive result because on the face of it, the quantum random energy model is more random, it's more disordered, whereas these disordered local Hamiltonians have this correlation in the disorder, which means that if I make the system size larger and larger, then the Fock-space height energies in a small volume around some site become more and more uniform. So this sounds like a situation where the disordered local Hamiltonian should not have an MBL phase, whereas the random energy model should, but it's the other way around. And in the next part, using this classical percolation proxy on the MBL, I'm going to present a heuristic picture for this. But I'll be happy to take any questions about the self-consistent theory if there are any at this point, or even later.
So Sthitadhi,
right.
It might be a good
Sure.
idea for you to go on because we are already at 5:05. I know we asked a few questions, but
Sure.
maybe you can take 10 more minutes, and so that way that's why I'm saying don't stop for questions now. Go ahead. Yeah.
Okay, great. Okay, 10 minutes is perfectly fine. All right, so how do we define a classical percolation problem on the Fock-space? So what we do is we write down our favorite Hamiltonian on this Fock-space graph, and we say that we will have a link between any two Fock-space sites present if the matrix element, Tik, is larger than the energy difference between the two. If it's greater than 1, we keep the link. If it's less than 1, we actually remove the link. And that defines a bond percolation problem on the Fock-space graph for me. Now, this is not a standard percolation problem. I'm not asking whether a cluster can propagate from one side of the Fock-space graph to another side of the Fock-space graph. Rather, what I'm asking is that what about the statistics of connected clusters on the Fock-space? In particular, if I take a typical cluster size, I can show that this scales as the Fock-space dimension to some power alpha. And the question then is, how does alpha vary with the disorder strength? So what we find is, okay, so this is a problem which for this particular model, we can solve the classical percolation problem analytically and exactly, even though there are these strong correlations in the bonds present. But the essential result is that below a certain disorder strength, the typical cluster size is linearly proportional to the Fock-space dimension. What that means is that the cluster actually has a macroscopic fraction of the Fock-space inside it. Whereas if I go to the localized or beyond a critical disorder, which we call the proxy to the MBL phase, the goes as the Fock-space dimension to some power alpha with alpha less than 1. Now, this is in direct analogy to how MBL eigenstates behave on the Fock-space in terms of their IPRs or their participation entropies. And then we have a critical point here, and this critical point actually, something we can find exactly. And at the critical point, the critical exponent is 2. Now, this is in some sense good news, because remember that at its heart, this is a one-dimensional problem, and we expect the critical exponent to satisfy the Harris CCFS bounds, which means that nu should be greater than 2 over d. In this case, it is, which is good news. There is some amount of debate over there because even the largest exact diagonalization results actually don't quite show a satisfaction of the Harris bounds and so on. But okay, so this is good for us because we can compute the exponent exactly and we can show that it's 2. And the point here is that when this Fock-space fractures in this percolation language in the MBL phase proxy, then what really happens is that some of the spins or a finite density of the spins in the system actually freeze. So you can identify some spins which have the same orientation in all the sides of this cluster. Now, how does that actually give us any insight on the effect of correlations? It does so in the following way. So let's first look at the quantum random energy model, and let me partition my Fock-space into 2 parts. And let me fix a particular spin I, which is up in one part of my Fock-space, and the same spin is down in the other part of my Fock-space. Now, all the links that go between these 2 parts of the Fock-space basically involve the flipping of this particular spin that I have fixed and colored in red. And these ellipses basically show the rest of the sites, rest of the real space sites. But now, on the quantum random energy model, all the energy scales associated to flipping this particular spin are independent. There are exponentially large number of them. So, in the thermodynamic limit, it's impossible to avoid at least one resonance. At least one of the links in the thermodynamic limit is definitely going to be active. And that is all that you need to force delocalization, because once you can flip this spin in red, you can actually join the 2 Fock spaces and it becomes again one large cluster. And you can sort of run this argument for multiple spins and show that you actually don't have any fracturing of the Fock space in the quantum random energy model, which is consistent with the fact that it has no MBL phase. In fact, although this is a classical calculation, you can do a sort of a quantum calculation using the forward scattering approximation, which is what this paper by Antonello Scarticcio and his collaborators did. And basically, they had the same idea, except that here the resonance has a classical meaning. In their case, the resonance had a quantum meaning, that one resonance is enough to actually delocalize your quantum random energy model. But now let's turn to the disordered spin chain. Now, if I want to flip this particular spin again in red, I need to worry about what the neighbors are doing, but I only need to worry about its nearest neighbors because that's what they're in the Hamiltonian. So as I was saying, so no, sort of in the part of my talk about correlations, there are only 4 energy scales that govern the possible flipping of this red spin. And those 4 or those 4 basically energy scales come from the 4 possible configurations of its neighbors. So even though there are an exponentially large number of bonds going between or links going between the 2 parts of the Fock-space, what you actually have is only 4 energy scales controlling all of them. So that is something you can make off resonant even in the thermodynamic limit, because in order to freeze this particular spin, you only need to make an order 1 number of energy scales off resonant, which is something you can do in the thermodynamic limit. And this is how correlations actually help in defeating the high connectivity of the graph. And this is sort of a heuristic picture for why our self-consistent analytical theory based on the propagators told us that you can have localization in the presence of strong correlations, and you cannot have localization when there are no correlations. And that basically ties, at least in our opinion, that basically ties these 2 pictures together. And the central result is that in order to have MBL, you need to have maximal correlations in the disorder. Okay, so I must add that not all hope is lost for the quantum random energy model. It can still have an MBL phase in the presence of constrained dynamics inspired from classical classes. This is just an advertisement. I'm not going to talk about this. It's a topic of an entirely different talk. But in the next 2 or 3 minutes that I have, let me quickly go over to this Anderson localization problem. And here, the idea was that we actually look at an Anderson localization problem, a single particle problem on a tree. A tree is simple for reasons I'll come to, where what we do is we will put disorder correlations. Now, when the disorders is not correlated, it's completely uncorrelated, it's known that the critical disorder goes as k times log k, where k is the branching number of the tree. What we will do is we will impose disorder correlations of a form which goes as the function f, which is a function of the distance on the tree between 2 sites I and j over L, where L is the number of generations in the tree. And this is basically trying to mimic the fact that on the Fock-space you have a polynomial of R over N for the p-spin system. But the point is that it's a function of R over N. Now, on this tree as well, you notice that with increasing system size, the energies of nearby sites actually become more and more uniform, just like in the MBL problem. And hence, it's not, forget about the MBL problem. On this Anderson localization problem, the presence of a non-ergodic phase is not remotely obvious. But the reason we still study this is because now you can write down the self energy on the tree exactly. This is actually an exact result. There are no higher order terms. But this SI1 with the subscript or superscript 0 basically means that it's the self energy of the site I1 with the site I equal to 0 removed. What that means is that SI1 is the self energy of, again, of a root site of this subtree. But what that means is that you can basically write it in terms of a continued fraction, and take it to all orders. And instead of trying to do a self-consistent theory here, what we look for is the convergence properties of this continued fraction. Notice that it actually takes into account all the correlated site energies, and this treatment is formally exact. So without going into the details, the upshot is that you indeed have a localized phase. This is what the phase diagram looks like. You have a localized phase, you have a delocalized phase. This localized phase, again, is not your conventional Anderson localized phase. It's a non-ergodic phase with fractal-like character. So one could say that, well, in the context of Anderson localization, it's more apt to call this a fractal state, but at least we know what's going on here. And you indeed actually have a localized phase. The nice thing here was that we didn't have to stop at some order and do a self-consistency, but we could actually take it to all orders and look at the convergence of the continued fraction. So with that, let me summarize. So this, again, the central point was that in disordered local Hamiltonians, you actually have strong correlations in the effective Fock-space disorder, which are maximally correlated in the sense that nearby sites or sites at finite distance are completely slave to each other in the thermodynamic limit. And that turns out to be a necessary condition for stabilizing an MBL phase. I basically tried to argue in favor of this in three ways. I talked about calculation based on propagators on the Fock-space. I talked about a classical percolation proxy, which gave you a physical picture for what happens with the correlations. And then I sort of looked at an Anderson localization problem on a tree with a similar motivation. Of course, the important outstanding questions are that what can I say about the nature of the transition from a theory based on the Fock-space and compared to the phenomenological treatments, some of which are now beginning to predict that the transition may be a bit like KT, but not exactly KT and so on. So of course, that means that you need to go beyond these mean field type theories. And the second point, which is something that I am more actively looking at right now, is that how to connect these theories on the Fock-space to microscopic theories on the real space, because I know the arrangement of spin configurations on the Fock-space. There is a certain amount of correlation there as well. So how can I incorporate that into my Fock-space propagator and talk about, say, transport, or how do local autocorrelations in spins decay with time and so on and so forth. But these are things that I'm doing currently. So with that, yeah, thank you for the attention and thanks for the questions. I'll be happy to take more if there are.
Thank you, Sthitadhi. Thank you for the very nice talk. I have just one question which I find, because if you just take a model on 1D lattice and you actually don't work in the Fock-space, but you just think of the local coupling spin models and make them correlated disorder. Okay. Then of course we know that if I make the correlation very large, the system actually goes out of MBL phase. I mean, one way to see that is that if you make it infinitely correlated or extremely correlated, that basically means essentially every whatever coupling is the same. And that's essentially a translation invariant system, to be fair.
Right.
So what you are saying is kind of opposite of what would one would expect instead of thinking in Fock-space if one was thinking of couplings in real space. So where does this, because it's extremely opposite, because I mean, okay,
Yes.
so you data, but the argument is much simpler that, infinite exact correlations would mean a translation invariant system. So how do you square these two things? One, in real space, it looks like opposite answers would be true. In Fock-space, what you are getting is something completely different.
Right. Okay. I mean, and this is something which I also sort of alluded to in the middle of my talk, that what we actually get is completely opposite to what you would expect, in the sense that the random energy model on the Fock-space is more random, yet it does not have an MBL phase. So the way we like to think about this is the following: that you gave an example of a 1D chain, but the 1D chain doesn't have to be special. If I can think of the Fock-space as some graph on real space, then what the example that you gave still holds, that the energy differences are becoming more and more uniform, So, but I think it's a bit more to it. There is a bit more to it than that, because there is this other sort of correlation also sitting there, which is that you have, and these two are not independent of each other, that you have the same energy scales controlling the flipping of a given real space site. So, okay, so MBL is, okay, at its heart, it's a real space phenomena, because it's suppression of transport and so on and so forth. So I think that the way I squared this is how I presented the argument in the classical percolation section, which is that once you have these correlations, you actually reduce the effective number of energy scales in your problem. As a result, you actually have a fighting chance of making them off resonant so as to stop the wave function spreading on the Fock-space. So yeah, that's what I can say about this. I mean, for instance, in the quantum random energy model, you don't have this freedom, because all the energy scales are independent, and all you need is basically one path in the Fock-space to go through, and that's what this forward scattering approximation that I mentioned by Sthitadhi and company basically does. That, and if you have one path which goes through such that you can flip, all the spins, then you actually have joined your Fock-space together, and the eigenstate actually has a support on a macroscopic fraction of the Fock-space, and that's basically the death of MBL. So I think the way I squared this is basically having only an order 1 number of energy scales associated with an exponentially large number of links.
Okay. Any other questions from anybody else?
Sthitadhi, so is there any analog for this Harris criteria kind of things which would agree something with your this percolation kind of threshold results?
Well, my percolation results agree with the Harris bounds, right? Because the Harris bounds say that the exponent should be greater or equal to or greater than 2 over d.
Yeah, okay.
And my exponent was exactly 2. So, but yeah, I mean, this is sort of a question that I mean, that's sort of active in the community, which is what exactly is the nature of the transition? There is also a sort of more fundamental question that you can ask here, that because this is not a sort of conventional phase transition, this is an eigenstate phase transition, do you even expect the Harris bounds to hold? But okay, that's a question for a completely different
But
discussion.
you could construct those kind of Harris kind of arguments on the Fock-space as well, right? Because it has
no, I'm not so sure, because what D will you then, if you want to construct an argument on
Yes.
Fock-space, that's a whole different ball game.
Right. So the
It's not,
dimensions will, okay,
yeah.
yeah, you're right.
Right. There are some arguments saying that, okay, but these are old and these have been refined in the last few years, which is that you can sort of try to come up with some sort of a Harris type argument for the entanglement entropy, because the MBA transition is also an entanglement transition. It goes from a volume law to area law in the eigenstates. And I think there was a paper by Chris Lauman, Anusha Chandran, and Vadim Oganessian, I believe. And I think they sort of figured out in some way, not as rigorous as the original Harris bounds, that the bound probably is 2 over d. But then if the more recent works which say that the transition is kt like, not exactly kt but kt like, okay, then it's a different scenario, because then formally you have an infinite exponent. So yes, so the nature of the transition and the exponent is still very much under debate.
Okay, thanks.